Hi, I'm going to be talking about the photovoltaic effect, which is the process by which two materials can create an electrical voltage when they're struck by photons in light, either from the sun or from other source of radiation that has photons in it. So the best way to explain this phenomenon would be in the context of its most common application, which is solar cells, or solar panels, which convert solar radiation into electricity that can be used in houses and like buildings, anything that requires electricity. So first, the most common semiconductors used in making these solar panels is silicon. And this silicon has 4 valence electrons, and when it's in a big panel full of silicon atoms, it creates like crystal-like structures which are really strong and are highly stable, right? Because you have your silicon atom here, and each one has 4 valence electrons. And when it's surrounded by other silicon atoms, each with 4 valence electrons, they form bonds, and they share electrons with each other to fill up their openings. So they end up with 8 valence electrons. This state it's highly stable, and they aren't gonna like shift or move electrons or share electrons or anything else in this state. So what scientists do is, in one panel, they insert boron atoms, which have 3 valence electrons. So you end up with things like this, where you have the silicon atom here bonded to other like boron and silicon atoms. So you end up with structures that look like this, where these would all be silicon atoms around here. So these all have 8, and they're happy. But there's a boron atom in here, which can only share 3 electrons. So you end up with an opening right here, where there is no electron, and this silicon atom wants to fill up that spot. So there's a bit right there which doesn't have an electron. So that's one panel. Then in the second panel, you might use something like phosphorus, which has 5 valence electrons. And the problem here is when it's surrounded by, say, silicon, it's going to end up bonding, and it's going to fill up everywhere. But the problem is, with this type of bonding, there's always going to be one extra valence electron floating around there, either from a phosphorus atom or a silicon atom. And there's just nowhere for that extra electron to go, so it's just kind of stranded there. So you have 2 panels, one that's been doped with boron and one that's been doped with phosphorus. So you'll have the 2 panels lined up with each other. And this is what happens in a solar panel. There's a top layer, usually the one with the extra electrons, called this N, and this P. It's called a PN junction, and this creates a direct current in which the electricity can only flow in one direction. So here you have all the extra electrons. Put the little negative sign for electron. So those are the extra electrons. Then in this bottom panel, this is where the openings for the electrons are. And so these extra electrons are just stranded here, and they want to find like an atom, a nucleus that they can get to. However, there's just nothing in this panel, and they can't just like go wherever they want randomly, unless they can't really move anywhere until they are struck by the sun. The sun emits light, and light is comprised of particles called photons. And when the light reaches the solar panel, the photons can actually knock the electrons out from this panel, and the energy is absorbed by these electrons, and they finally have enough energy to get from here to the panel below them, which has the openings for them. So all of a sudden, this electron is gone, and like an electric current is made, because these electrons all move down. So these are suddenly filled up. This creates an electrical current. So once you're here, what's created here is actually an electric field in which there are like still positive holes for the electrons here, and then a bunch of electrons here. But when these like kind of the electrons move over and kind of join the holes that are for them, an electric field is created, and they can no longer cross over. So this is where photons come back into play. When they hit these like particles again, they can actually knock the electrons back into the N-type surface, and then the holes back into the P-type surface. So a way to get around this is by attaching it like a cable or something that allows the flow of electrons and particles to get back to their original state. And this is where you actually get the electrical current. And if you put like a light bulb right here, a resistor, you'll actually be getting there'll be a difference in voltage from here and here, which is what's going to create or the potential for work, which is what's going to create the actual electrical current. So the light hits one of the particles, it goes back, and then to get back to its original condition and to allow these to join together, it'll go through the cable, go through the resistor, and that's where it actually does the work and be useful electricity. And then it'll go back, and this will be positive again, and these will all be negative again, and basically it just goes back to its original state, where this one has all the negative and this one has all the positive. And then the process repeats. The electrons go towards positive electric field. Then again, these particles still want to get over it, but they can't because the field is blocking them. And the process repeats. So that's how solar panels work. And this is the photovoltaic effect. It's just the main way that solar cells actually work.